Hello, everybody. 3.2 logarithmic functions. Appreciate you watching. I love logarithms, so this is pretty exciting for me to get to talk to you about this. Uh, so here is the basic definition of what a logarithmic function is and how to convert between logarithmic to exponential functions. Um, you might notice a little a little change from what you saw with exponential functions in the last section. Now, the basic definition of a logarithmic function is it's considered the inverse of the exponential function. As you might see with um, what I wrote down here, you notice we have a base b of a logarithm, so this is the small number here, and an x right here equals y. And it's read as log base b of x. Log base b of x. That's how it's read. So if you want to write that down, log base b of x, I will expect you to be able to say, use your math words and explain that. And you notice here with the exponential function that if this is true right here, then this is true. What do you notice? The x and y are switched. Why? Because the logarithmic function is the inverse of the exponential. Okay, and we see this down below here in this graph I drew you. This is basically right here, as you hopefully remember from the last section, that's your exponential function, right? This is your logarithmic function. They are inverses of each other. I misspelled logarithm. There you go. So they are inverses of one another. So you swap the x and y value. So like here, that's supposed to be 0, 1, and here I'm calling that 1, 0. Yeah, and that continues on for a long time. I would recommend pausing this video to write down your basic properties of logarithms. I'm going to explain briefly why these are true. If I change number 1 to logarithm form, b to the power 0, well, as you know, anything that's 0 power is always going to be 1. Right? Same thing here. If I'm converting, your base is b, your exponent is always what the logarithm is equal to, and b to the first power is just going to be b. Same story here. Duh, b to the x is equal to b to the power of x. Number 4 will take a little bit of work, but if you have a base and exponent and you're throwing in logarithm form, right? The log base b of x, which is me just writing this exponent in logarithmic form. It's base b, x is there. It's what the exponential equation is equal to what? What's up top? Log base b of x. All right. You don't need to write down my explanations, but I just thought you want to hear it. And we got a few evaluating logarithms. All of these you should be able to do without a calculator. Dun dun dun. Which shouldn't be bad. Okay. So this one might be a little goofy here. So you see log base 9 of 81. If you get a problem like this and I say don't use your calculator, your goal is probably to get this number to have the same base as that. So 9 to what power gets you 81? That's 9 to the second. These two numbers are the same, so what's your answer? Whatever the exponent is, according to our rules. So that's 2. Also, according to our rules, if this number and this number are the same, then your answer is going to be whatever that number is. In that case, it's 1. So your answer is 1. As we established with the first example we did together, this number and this number are the same. I don't need to do anything with it. The answer is just whatever the exponent is, 3.2. This one right here, the last one's going to be a little bit more work, but we can do it without a calculator. So your base is 16. Whatever your exponent is, we don't know. So I'm going to make that y equals square root of 2. Square root's like saying what power? What half, right? Can we get 16 to be a base of 2? Yes, we can. 2 to what power gets you 16? 4. And then power to power, you multiply, so you get 2 to the power of 4y is equal to 2 to the power of 1 half. Set 4y equal to 1 half. Divide by 4, and you will get y is equal to 1/8. Now we got some common logarithms. Now, what is a common logarithm? If you don't see a number in the base, we assume it is log base 10. Okay, so if I just write log of x, assume it's log base 10 of x. Okay, but we don't need to say, just say log of x, okay? Because we assume if there's no number there, it's 10. And I think, why do we do that? Because we tens are easy to work with, okay? Because 10 squared is 100. 10 to the third power is 1,000, right? You just keep adding and taking away zeros or moving the decimal point over in terms of base 10. So they're pretty easy to work with and aren't overly complicated. So we have this first example here. So log of 10,000 is equal to what? 10 to the power of I don't know, look at x, equals 10,000. So how many zeros are we going to need to add, right? So if I start with 10 and I'm going to get to 10,000, so that's 1, 2, 3, right? And 4, because we need another 0. So how many times do I move over? 4, okay? Because 1 will get us the same value, then 2 is going to get us 100, and 3 is going to get us 1,000. 4 is going to get us 10,000. So x would be equal to 4. The second one is you do have to use your calculator for. I would not be that mean to give you a problem like this. The second one, if you throw log of 0.081 in your calculator, find the log button on your graphing calculator. It's there, I promise. Just keep looking for log. You can do it. You throw that in, you're going to get negative 1.09. And this last one, log of 0. You should know right away. No solution. Why should you know right away? As we stated in the beginning, this value right here should not be equal to 0. We stated at the very beginning. Or negative. Okay? Should not be negative, should not be 0. Okay? Here are some basic properties of natural logarithms. What makes a natural logarithm a natural logarithm? Well, whenever your base for your log function is a base e, that's when you just use ln instead. Okay? So ln is implying log base e. Okay, so anytime you see ln, think of this. But they're pretty much the same rules across the board. Okay, those 4 rules we had for logs is pretty much what you're seeing here with ln. And I think over time you'll realize that for some of you, you might find ln much easier to work with, and might appreciate them a little bit more. Let's do a couple examples down below here. So if e to the power of ln of 4. Now, if you remember, now you don't have to show me this part, but your ln is just like log base e, right? And anytime with our first 4 rules we did earlier, when those matched up, your answer is just whatever that number is. Or if you just want to look at the 4 rules we just showed you, anytime you have e to the power of ln, whatever this number is right there will be your answer. This one you have a little bit more work for. Now keep in mind, anytime you have an exponent denominator, you can rewrite it if you just flip the sign of the exponents. Now, anytime you see this lovely ln of e, they cancel, and you left with whatever the exponent is. So your answer would be negative 3. Time to graph logarithm function. So it's really hard to look at this and be able to graph it properly. So what I like to do is I like to change it to exponential form. So we have base of 2. I'm not going to put h of x in my exponent, but I'm going to change it to y. And then whatever this value is what the base and exponent equal to. So this is and this is something you have to mentally get by. I'm going to plug in values for y to get x, because that's what my exponent is. So if I put in 0 for y, x will be 1. if I put in a -1 for y, 2 to the negative first will be just 1/2. If I pick a bit bigger number, so 1 and 2, if I put 1 in, I get 2. I get 2 in, I get 4. So let's try starting with that. So 1 comma 0, 1/2 comma -1, 2 comma 1, 4 comma 2. And it'll look something like that. And we have properties for logarithmic growth and decay. I would recommend that you pause it and jot all these little tidbits down. Pretty self-explanatory. If you look at the graph we just did, which was a growth problem, you'll see that all these lovely things on the left column here do check out. All right, we got two examples right here. So, what transformation is happening with the first one? You'll translating 2 units to the right. So if you remember, like the original function for logarithms, you have an x-intercept at 1 comma 0. Now you move that over 6 spots to 7. So 2, 3, 4, 5, 6, 7. And your asymptote is going down there. And we'll slowly trickle up. You can use your lovely calculator to get it more exact. 'Cause I know it's base E, and I know that's not going to get you. It's going to get you a decimal value for this case. This other one here, plus 4. Excuse me. I'll start from the beginning. H of x is equal to natural log of x plus 4, all plus 3. So we're moving up 3 and left 4. So if I'm moving left 4, so my intercept that used to be at 1 comma 0 is now going to be moved over 4 and up 3. And your asymptote is now at x equal to -4, so it's never going to touch that value. And once again, slow increase. Cool. Appreciate you watching, and we'll see you in class.